Hi everyone. Today I'm going to present you my work, which is the LGADC, an innovative way to cluster cells in patients using latent directly allocations. So complex diseases are very challenging to understand, and mostly the transition between multiple steps toward the disease. So nowadays, high-dimensional data gives us the opportunity to study the heterogeneity in cells populations. So single-cell RNA sequences, as well as cytometry technique, revolutionized the field of life sciences by bringing some years ago an unprecedented resolution to study the heterogeneity in cells populations. However, high-dimensional data are complicated to understand, mostly due to the fact that they have a high number of variables. So we have to find a way to regroup these multiple matrices coming from different patients and identify some similarities and underlying structures for stratifications. So traditionally, what people do is that they have different patients and they can regroup the matrices of data and apply some dimensional reduction and clustering technique and identify some cells into the space and identify some group of cells. So here what we want to do is to develop a new method to cluster cells and patients simultaneously. So imagine we have different type of patients like lean, obese and obese diabetic patients, and for them we have different matrices of data. So by regrouping these matrices, apply some clustering technique and reducing the dimensionality, we want to find some clusters of cells associated to different type of patients and phenotypes of patients, and identify some phenotype of patients that are related to some phenotype of cells. So for this purpose, we used a technique called latent directly allocations. So the latent directly allocation is used in the natural language processing in the machine learning community, and as a brief case, imagine you have different documents and every document is defined by some words. So for example, you have document 0, which is composed of bread, document number 1, which is composed with avocado, document number 2 with plain, and document number 3 with a mixture of plain, avocado, and bread. So we can count the number of times each word is inside each document, and by applying the LDA, we can regroup, we can identify some words that are associated to different topics and identify some document related to the topics. And so we can separate the document into the space and assimilate each document to a topic. So now the idea is what's the point between a natural language processing technique and the biological or medical data. So here patients are considered as words because patients are collection of documents. And so collection of documents are composed of words, which is cell phenotypes. And here patients are documents, which is collection of cell, where cell phenotypes are considered as words. And so by using this continuous data, we can apply our technique, which is called LDADC, and we can stratify the patients. So this presentation is divided in 3 parts. So first I'm going to talk about the method that we designed, which is an introduction of a generalized statistical machine learning approach for cellular and host clustering, which is called a double clustering. Then I will show you some results on our technique on different simulated data to identify the ground truth. Then I'm going to show you the technique on multiple medical datasets from cytometry and genius data for AML datasets and microbiota datasets. So the method here of the LGADC, as I told you previously, is that we have different matrices of data where we have cells as rows and vectors as columns. And so by regrouping these matrices, we can concatenate these matrices, apply the Z-score and K-means clustering, and identify some labels for each cells. And so at the end, we obtain a bag of words for every patient. And so by applying the GIP sampling, which is the core of the LDA method, we can update the probability of a patient to be inside a topic and also a probability of a word to be inside a topic. And so we can investigate the probability of a word to be inside the topic, and also the probability of a patient to be inside the topic. So now we decided to simulate some patients, and so we generate different phenotypes with different markers. And so imagine we have two phenotypes and we have a vector of probability of 4. We can update this probability and apply our technique. And what we found is when the Euclidean distance is high, we can separate the patient with a high accuracy, near 1. When the Euclidean distance is equal to 0, we can't separate them with high accuracy, which is normal because an Euclidean distance equal to 0 means that patients are exactly the same. So now we decided to test our approach on 4 phenotype, and we redo exactly the same thing by switching the different probabilities, and we found that when the Euclidean distance is high, we can separate the patient with high accuracy, and when the Euclidean distance is low, we can't separate them with a high accuracy. So now we identified the ground truth on simulated data, and we decided to apply our method on medical datasets. And so first we applied it on the AML dataset, which is the acute myeloid leukemia one. And so the AML dataset is composed of 2,872 samples from flow cytometry standards coming from 359 EML and no-EML patients. We have 8 tubes of experiment, which is independent experiment, and are composed of different biomarkers. And it's come from the publications of Agrepur et al. In 2013. And so when we apply our technique, we found that we are able to separate the AML patients and no AML patients with a very high accuracy with tube number 4. And so we perform also great for tube number 6. But the thing here is that we have the information of the cells that drive these predictions. And so we can investigate the probability of a word, which is the cell phenotype, to be inside the topics. And so when we investigate the probability of a word to be inside the topics, we found that we have some phenotype of cells that are highly probable in the topic number 1 and topic number 0. And so when we set a threshold at 0.9 and select 1,000 cells of each phenotype from the topic number 0 and topic number 1, select the cells, we select the vector of fluorescence, we can apply a dimensional reduction and project it on a UMAP axis. We found that cells that are clusters into the space are on the left and on the right. And when we highlight the cells based on their topic attribution, we found that topic number 0 cells are on the left and topic number 1 are on the right. And so when we highlight the cell based on their condition, we found that on the left we have mostly cells that come from EML patients, while on the right we have only cells that are from normal patients. And so here what we found is that we have EML patients that are associated to cells involved in topic number 0, and topic number 0 is associated to different phenotypes of cells. So now we decided to test our approach on microbiota dataset, which is composed of 29 Crohn's disease patients and 66 healthy patients. And we have cytometry data from Crohn patient and healthy individual, as well as genius data. And so we can stratify the patients based on their cytometry data or on their genius data. And so here what we decided to investigate the probability of a patient to be inside the topic, and we found that we have a very high accuracy to separate the patients and using cytometry data or genius data. So now we decided to redo this technique 40 times and calculate the number of times each patient is associated into the same clusters, and we fixed the number of topics to 7. And what we found is that Crohn's disease patients are on the top left and they are highly sick patients, and we also find two mixture of clusters composed of healthy and Crohn's disease patients. And so when we highlight the patients based on their enterotype, we found that Bacteroides 2 patients are on the top left, while we found a mixture of different enterotype in the two other clusters. And so when we decided to use the genus data, we found that Crohn's disease patients are mostly on the left, while healthy patients are only on the right. And they form a continuum from the left to the right. And so when we highlight the patients based on their enterotype, we found that Crohn's disease patients which are associated to Bacteroides 2 patients are on the left, and Prevotella patients and Ruminococcacea patients are on the right, which is associated to healthy individuals. So now we decided to investigate the probability of a word to be inside the topic for the genus data. And here what we found is that healthy patients are associated to topic number 1, while Crohn's disease patients are associated to topic number 0, because topic number 1 is highly enriched with healthy individual, while topic number 0 is highly enriched with Crohn's disease patients. And so when we investigate the probability of a word to be inside the topic, we found that topic number 0, which is associated to Crohn's disease patient, is highly composed of bacteria that are associated to Crohn's disease and have been identified in the literature as key bacteria that drive the phenotype of Crohn's disease patients. So as a conclusion here, we developed a novel method to stratify the patients. It addressed the problem of double clustering by using a Bayesian approach. It's an unsupervised learning method, and it provides a link between cell phenotypes and patients' outcome. And we also show that a networking approach is possible. However, one of the major critical points is that there is no guarantee of the Gibbs sampling convergence after multiple iterations. And so as a perspective, we want to develop the software for clinicians and biologists to test the method on different cohorts that we have on the lab, mostly the Karma cohort and the Metacardis cohort. And we want to develop a hierarchical method to search for a hierarchy on cell phenotypes. And this work is now inside a paper that is in review in bioinformatics. And so I want to acknowledge all the people of the lab. On the left, you have the NutriOmics peoples, and on the right, my advisors. So thank you for your attention, and I hope this presentation was great for you.